Deep within an electrical grid, balance is everything. Every second of every day, the amount of power flowing into high-voltage lines must exactly match the amount of power consumed by millions of homes and factories. If a sudden surge in electricity demand occurs, or if a major transmission line fails, the steady beat of the system begins to stumble. The overall grid frequency drops below its standard mark of 60 Hz, threatening to trigger wide protection trips. For over a century, grid operators counted on massive physical machines to survive these sudden energy shocks. Thermal power plants ran heavy steam turbines that weighed hundreds of tons. These giant steel rotors turned continuously at thousands of revolutions per minute. Because of their immense physical weight, they possessed a natural mechanical force called physical inertia. They resisted any sudden change in rotational speed, acting like a heavy mechanical shock absorber for the entire regional network. When an unexpected loss of power generation happened, the spinning momentum of those giant turbines kept them turning for a few precious seconds. That physical weight pushed stored kinetic energy into the lines automatically, preventing an immediate system crash. This built-in buffer gave automatic control systems enough time to adjust steam valves and bring extra generators online. The physical weight of heavy machinery kept the entire electrical grid safe from instant blackout events. That physical anchor is now vanishing from modern energy networks. Across the world, older fossil fuel plants are closing to make room for clean generation. Solar panels and wind farms are spreading across landscapes, generating vast amounts of carbon-free electricity. But solar panels have no moving mechanical parts at all, and wind turbines use electronic systems that isolate their spinning blades from the main network. They do not naturally supply heavy physical weight to the electrical grid. Without those heavy spinning turbines, the total inertia on the grid drops sharply. When a power plant trips or a line fails on a low inertia grid, the frequency drops far faster than it used to. A quick loss of power balance that once caused a minor dip can now cause a rapid frequency crash in less than a single second. Traditional backup systems simply cannot react fast enough to catch the fall before safety relays trip. The answer to this growing challenge lies in power inverters. Solar panels produce direct current power, while modern homes and factories run on alternating current power. Power inverters are solid-state power electronic units that take direct current and transform it into high-voltage alternating current electricity. As clean power expands, these high-power electronic devices are becoming the primary gateway connecting renewable energy sources to the shared electrical grid. In the past, power inverters were designed strictly as grid-following devices. They listened to the electric pulse of the grid and matched their output frequency to whatever signal traditional power plants were creating. They acted like quiet passengers on a bus, leaving all the heavy lifting of grid frequency regulation to old spinning turbines. If the main grid frequency fluctuated rapidly or collapsed, passive inverters simply disconnected themselves from the network. When grid-following devices supply only a small part of total energy, this passive design works fine. But as renewable energy integration reaches high levels, having most power sources act like passive passengers creates serious danger. If a sudden disruption occurs, thousands of older power inverters might shut down all at once to protect their internal circuits. This mass shutdown would drop even more power generation instantly, triggering cascading blackouts across whole regions. To fix this vulnerability, power engineers created grid-forming inverters and synthetic inertia. Synthetic inertia is a digital software solution that tells an inverter to act like a heavy spinning turbine. Instead of waiting for traditional power plants to guide the way, an inverter running advanced control software creates its own steady voltage signal. It stands firm like a digital anchor, actively supporting the frequency stability of the whole system. When the grid frequency drops suddenly, an inverter with synthetic inertia notices the change in less than a single millisecond. The internal software calculates how a heavy steel turbine would react to that sudden physical force. It then commands connected energy sources, such as large battery storage banks, to release an immediate surge of power onto the electrical grid. This quick injection mimics the physical momentum of a heavy rotor. This rapid digital response halts the rapid fall of frequency before it triggers safety shutoffs. Synthetic inertia does not rely on physical weight. It relies on high-speed measurement algorithms and rapid power electronics. The digital response is so fast that it can stabilize grid frequency drops long before a physical turbine could even begin to slow down. It turns silent silicon chips into active grid defenders. Inside modern power control centers, operators monitor digital screens tracking real-time frequency curves down to tiny fractions of a hertz. In a traditional low-inertia system, a sudden plant loss caused the line on the screen to dive steeply downward. Today, in regions backed by advanced battery storage and smart power inverters, that same loss produces only a slight, controlled dip. The invisible digital buffer catches the system instantly. Battery storage systems are essential for making synthetic inertia work effectively on a large scale. While solar panels need sunlight and wind turbines need breeze, battery banks hold electrical energy ready for instant release. When connected to grid-forming power inverters, a battery farm can discharge megawatts of power in milliseconds. This combination creates a flexible reserve that handles grid frequency regulation faster than any fossil fuel plant ever could. The magic of synthetic inertia happens inside microscopic control loops running on digital signal processors. Millions of times per second, the processor measures line voltage and current waveforms. When it detects a disturbance, it adjusts the fast switching of internal power transistors. By modulating these electronic pulses, the inverter adjusts its power output instantly, pushing back against frequency drops like a compressed mechanical spring. Implementing this technology across vast geographic regions brings real engineering challenges. Different grid-forming inverters must work together without fighting each other across transmission lines. If thousands of scattered battery inverters react to a minor voltage dip in slightly different ways, they could create destructive electrical oscillations. Engineers must tune control software precisely so every device acts as part of a single, harmonious digital choir. Islands and remote regions were the first places to prove the power of synthetic inertia. Places like South Australia, Hawaii, and isolated island grids faced constant blackout threats as clean energy adoption grew. By installing large battery arrays with grid-forming power inverters, these regions stabilized their local power grids. They showed that high levels of renewable energy integration could exist alongside rock-solid grid stability. This shift from physical weight to software controls marks a historic revolution in power engineering. For more than a century, electrical engineering was defined by copper, iron, and heavy spinning metal. Now, electrical grid stability relies on code, fast sensors, and power semiconductors. Physical momentum is being replaced by digital speed, allowing power systems to operate far more efficiently than old thermal power stations. During extreme weather events, when cold snaps or heat waves stress energy networks, synthetic inertia proves its value. When traditional generators trip unexpectedly under heavy load, smart power inverters step in within milliseconds to keep the balance. They protect hospital power grids, industrial lines, and residential neighborhoods from cascading failures, keeping lights on when the broader network is under extreme stress. Modern power inverters can also provide virtual damping alongside synthetic inertia. Damping acts like a shock absorber that smooths out fast electrical oscillations after a short circuit or lightning strike. By combining synthetic inertia with virtual damping, grid operators give the electrical system a dual layer of protection. The grid becomes resilient, flexible, and capable of self-healing during sudden power shocks. Out in suburban substations and rural energy parks, these high-tech systems operate in total silence. There are no roaring steam vents, no vibrating floors, and no glowing fires. Inside gray metal cabinets, bank after bank of power inverters silently converts and shapes millions of watts of clean electricity. They maintain the exact frequency heartbeat of modern civilization without a single moving mechanical part. As world energy systems aim for total decarbonization, the combination of renewable energy, battery storage, and synthetic inertia becomes vital. It removes the long-standing technical barrier that limited how much clean power a regional grid could safely handle. Power grids no longer need to burn coal or gas just to keep heavy turbines spinning for basic frequency stability. The electrical grid is evolving from a giant mechanical machine into an intelligent, software-defined network. Through the power of advanced inverters and synthetic inertia, we can stabilize the power grid while phasing out fossil fuels. The silent, lightning-fast precision of silicon chips is keeping our energy clean, our frequency steady, and our world connected.